Okay, so in the last class, we are talking about the gradient of a scalar quantity and what is the physical meaning of the gradient. What kind of physical information or the importance of the gradient here. We said that T is your scalar. T आपका is any scalar quantity which can be a function of x, which can be a function of xy, or it can be a function of x, y, and z in 3D. And let's say it can have any random value. It can have, let's say, a form of this type. Can be any, you can imagine any kind of scalar quantity here. So now we said that if this is a point whose coordinates are x, y, and z. At this point, the value of this function is, let's say, t here. If I move from this point to another point, and imagine, rather than I'm writing it on the screen, so it's a two-dimensional surface, but imagine it being in a 3D. आपके रूम में कोई एक point से आप कोई भी दूसरा random point imagine कीजिए, and here you change your x by a small amount, you change your y also by a small amount, and you change your z also by a small amount. And it's not necessary आपका x में जो change होगा वो y में change होगा, जो z में change होगा, they have to be equal to each other. It's absolutely not necessary. Maybe you are changing x only by 0.1, y you are changing by 0.3, and let's say z you are changing by 0.12. You can take any small dx, dy, and dz. They don't have to be even equal to each other. And let's say at this point, the value of this scalar becomes t plus dt. Now from here to here, when you go from here to here, and if this is, let's say, your origin, with respect to origin here, if the coordinates of this point is x, y, z, and coordinate of this point is these coordinates here, then I can define this length as a vector quantity, and that vector quantity is basically this number here. And the magnitude of this vector quantity is, of course, going to be given by the number, this one, from your vector information that you might already know. Now, in the last class, we said that I can write dt, which is change in this scalar quantity when you go from this point to this point in this form. This was where we stopped in the last class. We said the small change in this scalar quantity dt would be equal to delta t dot dl, where dl is the change in the variables x, y, and z. So this was where we stopped in the last class. Now let's talk about the dot product here. I can write this as right. Now, dl, if you keep dl fixed, let's do that. To simplify it, let's say आपने यहाँ से यहाँ, imagine it to be first in just number only. Let's say यहाँ से यहाँ आपने 2 centimeter move किया from this point to this point. You can move 2 centimeter here also. You can move 2 centimeter here also, in this direction also. There can be a very large number of ways in which you can move 2 centimeter. And this DL basically tells you that change in the length. Imagine yourself standing in the center of the room or somewhere in the room, and then you can take a step size of, let's say, 15 centimeter in a very large number of permutation and combination in the room. Now, if you pick this step size to be constant, that means you are saying that your DL, which basically represents your step size, is fixed. Now, theta is the angle between this term, which is your gradient, and DL here. इन दोनों के बीच में जो एंगल होगा वो cos थीटा होगा. ग्रेडियंट जो होगा, इस वाली, अगर आप सिंपली ये वाला फंक्शन ले रहे हैं तो यहां से आप इसका ग्रेडियंट कैलकुलेट करोगे, you will see your outcome is going to be a vector quantity. जिसका क्या होगा, एक मैग्नीट्यूड भी होगा और एक डायरेक्शन भी होगी। And theta is the angle between the direction of this gradient here and dl. Now, if you keep dl fixed, this dt here, dt which represents the change in this quantity, your dt is maximum when theta is 0. Because when theta is 0, cos theta is 1 and your dt is equal to simply product of these two terms here. When theta is 0, this means that your gradient, this and dl, they point in the same direction. Right? So, when they point in the same direction, your dt is maximum. This is what you are saying. So this basically then means that your gradient points in the direction of maximum increase. In function t. Look here, again, I am saying, अगर आप dl को fix कर दो, imagine a hypothetical case, अगर आप हिल के टॉप पे खड़े हो, हिल के टॉप से अगर आप नीचे की तरफ लुक करो, there are infinite different ways in which you can take a step down. बट एक पर्टिकुलर डायरेक्शन ऐसी होगी जिस डायरेक्शन में आपका जो स्लोप है वो स्टीपेस्ट होगा, and that particular direction is given by the gradient here. अगर imagine you are standing on a hill here, अब आप इस हिल के टॉप पे चढ़ने के लिए you can climb from here, you can climb from here and you can climb from here. जब आप यहाँ पे हैं, you simply let's say have to travel 10 centimeter, which you can travel from here and here and here. बट किसी एक डायरेक्शन में आपका स्लोप मैक्सिमम होगा, वो स्लोप किस डायरेक्शन में मैक्सिमम होगा, दैट वुड बी गिवन बाय द ग्रेडियंट ऑफ द फंक्शन. अगर आप इस हिल की हाइट के लिए कोई इक्वेशन या कोई स्केलर फंक्शन लिख सकते हैं, तो उस स्केलर फंक्शन का अगर आप ग्रेडियंट ले लेते हो, देन ग्रेडियंट इज गोइंग टू पॉइंट इन द डायरेक्शन ऑफ मैक्सिमम इंक्रीज इन द फंक्शन ऑफ हिल, which is going to be a scalar quantity. Because you are saying that your dt is maximum when your theta is 0. When your theta is 0, this term becomes equal to 1. When your theta is 0, that means you are saying gradient and dl, they are in the same direction, which basically means that अगर आप same dl के लिए अगर gradient की direction में move करोगे, तो आपके dt में जो change होगा वो maximum change होगा. Hence, gradient points in the direction of maximum increase in the scalar function. This is the physical significance of the gradient. कोई भी स्केलर फंक्शन दिया हो, उसका आप ग्रेडियंट कैलकुलेट कर दो, ग्रेडियंट will point in the direction of maximum increase in the scalar function that is provided to you. This is the physical significance of the gradient. Anyone has any doubt in it?
Ma'am, theta is the angle between dl and
this gradient here.
Okay, ma'am.
Now it points in the direction of maximum increase in function t. और अगर आप, because gradient is a vector, अगर आप इसका मैग्नीट्यूड कैलकुलेट कर देते हो, तो वो मैग्नीट्यूड देगा, वो आपको स्लोप देगा इन दिस डायरेक्शन, जिस डायरेक्शन में आपका मैक्सिमम इंक्रीज होगा. Gradient itself being a vector quantity, magnitude और direction दोनों है. Gradient की direction is going to point in the direction of maximum increase in the scalar function, whatever scalar function you are considering. Magnitude of the gradient is going to give you slope in that direction of maximum increase. Now, if your gradient is 0. What does that mean? अगर आपका gradient है वो 0 है किसी भी एक point पे, what would that mean? Similar, go back to one dimensional function. अगर आपका one dimensional function होता है, अगर किसी भी point पे you say that its derivative is 0, that's how you calculate the position of maxima, right? Or minima or point of inflection. Similar is the case here. If your gradient is 0, that means this corresponds to either the position of maximum or minimum, or maybe it's a shoulder. Shoulder means if you have a function which has something like maximum here, but something like this. So even though your maximum is here, but then this will be basically the shoulder of this function here. So if you want to, for example, if you are given a function here, let's say you are given the height of the hill of this form 3 times x square z minus, let's say 5 times x y z plus 16 times z y. Now, if you are asked to calculate the location of the tip of this hill, simply you have to calculate the gradient and put it equal to 0. जहां पे इसका gradient 0 होगा, that value of x and y would basically give you the position of maximum, which will be the top of the hill. This is the physical meaning of the gradient. Now let's talk about the other two terms. The second term is if you take the dot product of this del with the vector quantity. This is called as divergence.
Ma'am, can you please show the last slide?
हाँ जी बच्चे.
Ma'am, can you please explain what is shoulder?
You can have a minimum of a function, and there could be some other places where there could be a small dip in the function. Those places of small dips are called as shoulders in the function.
Done,
Coming
ma'am.
back to the divergence, if you have any vector quantity, and let's say your vector has 3 components, x component, y component, and z component. As I said before, del dot v, being a dot product, your outcome would be a scalar quantity. This divergence, the literal meaning of divergence is how much something is spreading out, right? You might have heard the word converge, something converging and something diverging, right? So divergence is basically if you calculate the divergence of any vector quantity, it tells you how much your vector is diverging from the point in question. This is the physical meaning of the divergence. It tells you how much your vector, which is given to you, diverging or spreading out from point in question. An example of this is simply, let's say you had something 3xy, x unit vector plus 2y, y unit vector plus 3 times x, y, z unit vector. अब अगर आप इसका डाइवर्जेंस कैलकुलेट करते हो इस वेक्टर का, which would be calculated in this way. आप कैलकुलेट कीजिए, you'll get 3y plus And then with respect to y, you will get 2 plus with respect to z, you will get 0. So you'll get 2 plus 3y. Now, if I want to calculate the value of this function at certain particular value of x, y, and z, let's say I want to calculate it at 0, 2, and 5. These are my x, y, z coordinate. Then the value of this function at this particular coordinates will be 2 into 3 times 2. 3 times 2 is 6 plus 8. If this number is
Ma'am,
positive, that means your vector is spreading out at this point here. If this would have been negative, let's say I would have wanted to calculate it at 0, -2, and 5. Then this number would have come out negative here. Then here your vector would have been converging. And when this number comes out to be positive, you say that your vector is basically diverging at this particular point. जब तक आप पॉइंट नहीं स्पेसिफाई करते हो, आप डाइवर्जेंस नहीं कैलकुलेट कर सकते हो. How this information is useful? Let me show you let me draw a couple of figures here. Suppose you have a positive charge here. आपके पास में कोई positive charge है, right? So what would happen to your electric field lines at this positive charge? They will be outgoing, right? Your positive electric field would be larger close to the charge, and it will get smaller as you move away from the charge. So on. And you can draw these lines almost everywhere, right? Now what would happen if you consider any point here? अगर आप यहाँ पे कोई भी या आप consider the point at the charge itself, at the positive charge itself. Will you say that your electric field is diverging at this location of the charge, or is it converging at the location of the charge? What would you guess at the first?
diverging.
It is diverging at that point, right? So all the positive charges are the points of the positive divergence. Agar ye negative charge hota, then your electric field lines would have been coming inside towards the negative charge, and your negative charges would have been points of negative divergences. But you can have any typical scenario. For example, I can have an electric field in this way also. Imagine all these arrows to be of the same size. If I give you a vector which looks like this, and again, consider that all the arrows, they are of the same size. Now, if you consider a point somewhere here at any point, remember always electric field line or any magnetic field line, they are just imaginary lines. I cannot draw them infinite in number very close to each other. So that means the gap here does not mean there is no electric field present here. It's just that I cannot draw infinite number of lines, but nonetheless, the field is equally present there also. So now if I have a point here, let's say this point P here, what would be the divergence at this point? Will it be 0? Because I'm saying the electric field lines are exactly of the same size. That means the magnitude of electric field is exactly same. So there is as much electric field lines which are entering at this point, as much will be leaving from this point. And the net result would be 0 in this case. Imagine if you have, again, consider a point here, and let's say you have something like this. And let's draw one more in. Now, if these lines are, again, these are hypothetical lines. If these lines are equal, which are coming in, and equal number of lines are going out, then your divergence at this point would be 0. This point P, your divergence would be 0. But you can also have a point where you have a larger number of lines going out and maybe a very small number of lines going in. In that case, this will be a point of the positive divergence because you have more number of field lines going out as compared to the less number of field lines which are coming in. Hence, this will be a point of, again, positive divergence. Again, consider a case with increasing size of the arrows. So I'm saying that your electric field is increasing here continuously in this direction. If I place a point here, what would happen to this point if I talk about in this direction here? Is your divergence positive or negative at this point? Anyone has any information? Or does anyone want to answer this question? What would be your divergence at this point P?
Positive.
Yes, you will have a positive divergence. Again, just because if I'm saying that the size of the arrow represents the magnitude of the field, then the field is smaller here and the field is larger here. So it is possible that maybe you had a positive charge here. यहाँ पे आपका जो field आया वो आपका field less था. इस positive charge के बाद में आपका जो आगे field गया वो stronger field होगा. And hence this point is then a point of positive divergence. So that kind of information about any field, and remember your fields are vector quantities, is given by the divergence. You can have your divergence positive. If your divergence is positive, that particular points are called as sources. If your del dot V for any vector quantity comes out to be a positive number, then those are called as sources. If your divergence comes out to be negative, then those are called as sinks. And if your divergence is 0, then these kind of fields are called as solenoidal fields. Your magnetic field is an example of solenoidal field. Remember, magnetic monopoles cannot exist. So if you take any point, there will be as many magnetic field line entering, as many magnetic field line will be leaving that point. Because you cannot have a separate magnetic north pole or a separate magnetic south pole. And that is not the case with electric field. Electric field where you can perfectly have a positive charge separate and a positive charge negative also, sorry, a negative charge also. So for electric field, you can have your divergence as positive or negative. But for your magnetic fields, your divergence is always going to be 0. And if your divergence for any field or any vector quantity is 0, then that vector field is called as solenoidal field. That basically forms that it is kind of solenoid. That means as many number of field lines are entering at that point, as many field lines will be leaving that point. So that is meant by having a divergence positive, negative, or 0. Coming to the next part, which is if you take the cross product of
Ma'am,
then
Can you go back to the previous slide?
Anjanji, sure.
ma'am, and after this, one more previous slide also.
Ma'am,
Sure. Anji,
in the first figure where we have taken the positive charge, it is an example of positive divergence, right?
yes, this is an example of positive divergence.
Okay, ma'am.
Ma'am, here how you have written del dot V is equal to 3y plus 2 plus 0.
क्योंकि आप इसका इसके साथ इस I have taken one specific example. I said, let's say that your vector is represented by this function here.
Ma'am, shouldn't it be 3xy plus 2y plus 3xy? Like,
No, it's a vector, right? You have x. जब आप इसका इसके साथ dot product कराओगे यहाँ पे, this is a dot product, right?
yes, ma'am.
तो आपके साथ सिर्फ जो x cap के साथ dot product 1 आएगा ना? So you will
Yes,
have
ma'am.
basically curly by curly x of 3xy.
Okay, ma'am.
तो आपके पास 3y बचेगा, right?
Okay, ma'am. Yes, ma'am.
हाँ जी,
Understood.
हाँ जी. And similar for the rest of the terms here.
Ma'am, please tell one
मैम
example
यहाँ
of
पे
negative divergence also.
Negative divergence.
Yes, ma'am.
नेगेटिव
Hanji.
चार्ज मैम.
Yes, negative charge is a point of negative divergence.
Okay, ma'am.
मैम आपने
Mathematically,
पिछली वाली स्लाइड में पॉजिटिव के आगे क्या लिखा था?
पॉजिटिव चार्ज, अगर आपका पॉजिटिव डाइवर्जेंस होगा, उन पॉइंट्स को सोर्सेज बोलते हैं.
ओके ओके मैम.
It's a simple vector product. You can again take V as a vector, which will have three components. Cross product simple है, जो हमने last class में discuss किया था. So I'm not going to write the expression for the cross product. You can go back and check that. Physically, now as the name suggests, curl, it tells you how much your vector is going to curl around. That information is given by del cross V. Now, how do you intuitively tell if the curl is zero or non-zero of a vector quantity? Let's go back to the previous examples here. Let's take this example first, where all the arrows are of the same size and we said the divergence is zero. If all the arrows are of the same size, then you're saying that your field is of constant magnitude in this region here. Now, if you are given this kind of vector, imagine placing a paper boat on it. यहाँ पे आप एक paper boat जो है very small size की, imagine कीजिए you have placed a paper boat here. If the paper boat starts to rotate, then this field which is shown here will have a curl in it. But if the paper boat does not rotate, that means the curl is going to be zero in that case. For example, in this case, you are saying that you have the constant amplitude of the field that is present here. If you place a paper boat here, it is going to just simply stay there, right? There will be no rotation or no curling around of this paper boat in this case. Similarly, in the second case, where you had the arrows of increasing size here, again, if you place a paper boat here at any point, a very small paper boat, it will not be rotating here also. If it's not rotating, that means the curl of this vector field, इस vector field का जो curl होगा, that is going to be zero. I'll show you some of the better figures which I have in the PPT. Just give me a second. At all these points, imagine placing a paper boat. There might be a translatory motion. Translatory motion means that your paper boat can simply move in the forward direction. That does not mean it has some curl. Unless it starts to rotate, the curl of the vector is going to be zero. If you place a paper boat either here or here or here, in all those three fields, it is going to be not rotating in any of the cases here. But if I show you another diagram here, imagine placing a paper boat in these cases here. Now, if I place a paper boat, let's say here, in this field here, I'm saying that the size of the arrow here represents the magnitude of the field. So that means the field is continuously increasing in this direction, right? यहाँ पे आपकी arrow small है, फिर larger, larger and larger होती जा रही है. So what would happen to the paper boat if you place a paper boat here? उसके On this end of the paper boat, the force would be less. On this end of the paper boat, the force would be much larger. If you hold a pen in your hand and on the one hand of the pen, you apply less force. On the other end of the pen, if you apply the larger force, you can rotate the pen, right? And similar thing is going to happen in this case also. And you will have a non-zero curl. In this case, because you are saying that the magnitude is increasing continuously. Now, if you place a paper boat here, on one hand, the force is going to act less. On the other hand, the magnitude of the force would be larger. And जिस end पे force का magnitude would be larger, it will start rotating the paper boat here. And then these kind of fields will have non-zero curl. And for this second case, it is obvious that it is going to rotate, because from figure itself, it seems like that whatever you put there, it is going to rotate. Your whirlpools in the water are basically points of extremely large curls. So by looking at the vector diagram, which is being provided to you, you can actually, looking simply at the figure, just imagine in your head placing a paper boat in that vector field and see if the paper boat starts to rotate or not. If it starts to rotate, that means that vector has some curl at that particular point. If it does not rotate, that means the curl is zero at that point for the vector. So this is the physical meaning of the curl of the vector. It is going to tell you how much the vector is going to rotate around the point in question. Remember, if you calculate the cross product, your outcome would be a vector quantity, which basically means that it will have a magnitude and it will have a direction. In the previous figure that I showed you, let me draw that here itself. If I have a vector, and imagine again all the arrows to be of the same size. We said if you place a paper boat here, it will start to rotate around. The curl needs to have the direction, right? It will have a magnitude and direction. How you can determine the direction? Again, use your right hand rule. Curl around your finger in the direction of the vector in which your vector is curling, and then the thumb will point out in the direction of the curl. Del cross V आपका thumb की direction में होगा. If your vector is represented, for example, in this way, you curl your fingers in the direction of these arrows, then your thumb will point in the direction of del cross V, and which will be out of the screen in this case. This is how you can get the information from del cross V. It will tell you at what point how much your vector is going to curl around. If you have this equal to 0, that means the curl is 0. If the curl is 0, that means there is no rotation in the field, and those fields are called as irrotational fields. For any vector field, for example, if you have electric field or magnetic field or any vector field, even if it is velocity, if the curl of that vector is 0, that means there is no rotation in that vector, and that particular kind of fields are called as irrotational fields. Now, I'm going to stop about the del operator right now. Now we are going to discuss two theorems, which I'm going to again use very repeatedly when we are going to derive Maxwell's 4 equation. So I would like you to remember those two theorems. First is fundamental theorem of divergences. And this is also called as Gauss theorem or Green's theorem. We'll not do the derivation of these theorems. I'll just simply tell you the statement of theorems, and I'll tell you the physical meaning of those theorems and why the mathematical expressions that I'm going to write, they are equal to each other. Before we do that, there is something which I would like to tell you. If you have a volume is always bound by surfaces, right? Imagine, for example, the room you are sitting here, the room in which you are sitting, it is probably bound by 6 surfaces. आपकी 4 walls हैं, एक floor है, एक ceiling है. अगर आप एक sphere लेते हो, then the sphere is bound by the surface area of the sphere, right? So everything which is in a volume, that is basically bound by the surfaces. Now let's talk about surfaces. Look at the wall around you. The surface on the wall is bound by lines, right? For example, if you have a surface, your wall here, this is the, let's say, surface area. And you will say probably the surface area, if this is A, this is B, the surface area will be given by AB. But this surface area is bound by a line here, which starts, you can start it from anywhere. It goes from here, it goes to here, it goes to here, and then it comes back to here. So your surface is basically bound by lines. So if you have a volume is going to be enclosed by surfaces. If you have the surfaces, then your surfaces are going to be bound by lines. And similarly, if you have a line, doesn't matter what kind of line, a line is going to be bound by 2 points. You will have a starting point and you will have an end point for the line. So these 2 theorems that I'm going to talk about, they will help you in conversion of volume integral to surface integral. And the second theorem, this fundamental theorem of divergences will help you convert volume to surface integral. The second theorem that we are going to talk about, that will help you in conversion of surface integrals to line integrals. You cannot go from volume to line. You cannot have any kind of theorem which will let you convert directly from volume to line. You can have something which will convert from volume to surfaces, and if there is a surface, you can have conversion from surfaces to lines. So the 2 theorems that we are going to talk about now will help you in these conversions, and which we are going to use further in Maxwell's equation. The first theorem basically says that if you have any vector, अगर आपके पास में कोई भी vector quantity है, if you have any vector quantity V, if you take the divergence of this vector, integrate it over the volume, d tau represents a small volume element. And capital V represents integration over volume. I'm just going to use one integral sign. That does not mean I'm integrating it over one variable. If I'm writing here V, that means I'm integrating it over the volume. And if your volume is something dx, dy, dz, that means you have to integrate it over x, y, and z. I'm not going to use 3 integration signs for that, even for the rest of electromagnetic wave also. So if you have the divergence, you integrate it over the volume, and this volume is going to be bound by the surface, and the value of this integral is equal to the value of the function at the surface. So this theorem basically says that the integral of the divergence, you have the divergence, you are integrating it over the volume, is basically equal to the value of the function at the boundary. This is what this simply says in words. You have the integral of divergence over the volume is basically equal to the value of the function at the boundary. For example, imagine a room. For आपके पास में, let's say, imagine a hypothetical room. In this room, you have a very large number of taps. And there are a couple of sinks also. Now, let's say the water is coming out of each of these taps, right? Divergence basically is positive at the sources. So if your water is coming out of these taps, then basically your taps are the points of positive divergences. Now, what you can do is that either, which is basically this term here, term 1 on the left hand side, either you can go at the each tap, measure how much water is coming out of the taps per second, and then you go to the holes and measure how much water is going into the holes. And then you do the proper addition and subtraction, and you find out what is the net flow of water per second here. The second way to do is, which is the right hand side, which is basically if water is coming out of these taps here, you just sit around the boundary here. The boundary which is properly closing all these points here, and measure how much water is going to flow out of these surfaces here, which is basically the boundary of this volume here. That would be your right hand side here. So this is basically a fundamental theorem of divergences. Either you can go to the individual source and measure how much is the flow, or you can simply measure the value at the boundary. And this is also called as Gauss theorem or Green theorem. It helps you in conversion from volume integral to the surface integral. Volume से आप surface integral में यहाँ पे convert कर सकते हैं. And we will use it time and again while deriving Maxwell's equation. So I would like you to write them down somewhere very safe where you can just go and watch it quickly, because now from this next lecture onwards, I'm going to use them almost 2 to 3 times in every single lecture. So this is the fundamental theorem of divergences. The next theorem is,
Ma'am,
Anji,
ma'am, why are we integrating divergence over volume?
because you're simply saying that how much is you are basically diverging from single point, right? हर एक सिंगल पॉइंट से आपका कितना डाइवर्जेंस हो रहा है, एंड आपके पास में एक लार्ज वॉल्यूम में कितना टोटल डाइवर्जेंस होगा. सो या तो आप सिंपली समेशन कर दो, समेशन which is basically will be equal to, let's say ये टैप में अगर पानी आपका Li आ रहा है, तो you can see simply summation Li, or I can say that I am going to integrate it over the volume.
Okay, ma'am.
हाँ जी. The second theorem is fundamental theorem of curls. I'll just take a couple of minutes and we'll be done. And this is also called as Stokes theorem. This theorem helps you in converting your surface integral into line integral. This basically says that you take the curl of a vector, integrate it over the area, and this would be equal to the value of this function at the boundary. Basically means that if you have a surface area here, and उस surface area में if you have very large number of curls, either you go to every single individual और सबका आप curl जो है वो measure करो, which will be your this side here, or you simply go to the boundary of this area which is given by the line here, and इस line के around आपकी कितनी curl है वो आप measure कर लो. They will be equivalent to each other, which is your second hand side. Remember, यहाँ पे आपके inside में जो curls होंगी, for example, अगर आप इस point पे और यहाँ पे देखें, in this direction your curl is in this direction, at here your curl is in this direction. So inside the curls will cancel each other out, and all the resultant curl will be at the boundary. And for a surface, the boundary is given by the line here, and that is why we have the integration over the line here. This fundamental theorem of curls or Stokes theorem helps you your conversion from area integral to the line integral, which is going to be extremely useful when we are going to derive Maxwell's equation. And again, I'm repeating that you need to write down this equation and the previous equation somewhere at a very convenient position, because I'm going to use them time and again from next lecture onwards. Anyone has any doubt in today's lecture?
Ma'am, and there